Okay, hello BC students. Okay, so basically I forgot to do the class recording for our, you're looking at the Friday, September 18th class recording. So I'm just gonna run through the stuff that we covered in class today anyway, just because we were working on that big related rates problem. So why not just record the whole thing? So yeah, I'm just gonna narrate through everything we covered today. So first we started with this, yesterday's exit ticket, the limit problem, which a lot of you guys did really well. So again, for this problem, we're looking at it, and I would say when we approach it, the first thing, our instinct is always just to plug in 0, right? What happens when we plug in 0? Well, when we plug in 0, let's see, we're gonna get the limit as x approaches 0 of e to the 2x. I'm just rewriting the problem here over tangent to x is equal to, well, we're going to plug in 0, right? So e to the 2 to the 0 minus 1 over tangent 0, right? So we're going to get e to the 0, which is just 1, minus 1 over tangent 0, which is just 0. So we're going to get 0 over 0. Cool, so that tells us absolutely nothing, right? We're like, okay, how am I supposed to solve for this, right? Well, luckily, 0 over 0 is also one of the most common indeterminate forms for us to use L'Hopital's. Cool, so the other one is infinity over infinity. So remember that. Infinity over infinity and 0 over 0 are two of the most common indeterminate forms, and these indeterminate forms are required for us to use L'Hopital's. So if we're going to use L'Hopital's, we have to have a limit that either is like 0 over 0 or infinity over infinity or that other list of indeterminate forms we looked at. So luckily we have 0 over 0, so we can apply L'Hopital's. We can apply L'Hopital's, L'Hopital's. Cool, and L'Hopital says, again, the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g of x. So basically the derivative of the top and the bottom. Sorry for my messy handwriting. And again, L'Hopital's only works if we have one of these indeterminate forms, which we do in this case. So let's see. In this case, the limit, I'm just rewriting the problem now. The limit is x equal to 0 of e to the 2x minus 1 over tangent x. And now we're going to derive it. So that is equal to the limit as x approaches 0 of 2e to the 2x over secant squared x. Now, how do we get this? Well, the derivative of e to the 2x, right? Well, we know our identity, right? The identity is that the derivative of e to the x is just e to the x. However, e to the 2x, we can also write e to the 2x, but we need to do a chain rule, right? Because we've got 2x in the exponent. So we got to multiply by the derivative of 2 to the x. So we're going to multiply this by 2. Remember, it's not always, like, we have to apply chain rule in situations where it's not just like a perfect polynomial or something. Even in the case of e to the x, in reality, what we're doing is deriving e to the x, which we get as e to the x, but multiplying by chain rule, the derivative of x is just 1. So we're actually doing a chain rule. It's just that the 1 disappears. So anyway, so in this case, 2 times e to the 2x, and the denominator, the derivative of tangent x, is secant squared of x. That is just an identity you're going to have to memorize. The derivative of tangent x is secant squared of x. So derivative of sine x is cosine x, derivative of cosine x is negative sine x, derivative of tangent x is secant squared x. So we're going to get this, right? We applied L'Hopital's. Cool, that's L'Hopital's. Now we're going to just plug in 0 again. So let's see if that helped. We're going to get, if we plug in 0, we're going to get 2e to the 2 times the 0 over secant squared of 0. Now 2 times e to the 0 is 2 times 1 over secant squared. Well, secant of 0 is just 1, so secant squared is just 1 squared. So we're going to get 2. Now, I think what might be confusing here is the denominator, which is secant of 0, secant squared of 0. And just to give a quick refresher, right? Secant is the reciprocal of cosine. Now, you guys probably just, how I remember all these things is just trying to memorize the unit circle again. So remember the unit circle, that's a terrible circle. The unit circle is like this, right? And then cosine, we're at 0, right? So secant squared of 0. Well, secant is the reciprocal of cosine. So let's just take a look at cosine. Well, cosine is this, and then cosine is x over r. So x, which is 1 in this case, and then r is also going to be here. So it's going to, cosine of 0 is going to be 1 over 1. Well, what's the reciprocal of 1 over 1? So we can find secant. The reciprocal of 1 over 1 is also 1 over 1. So secant is going to be 1. Secant equals 1. Cool. So we got that. We got 1 squared is equal to 2. Easy. Easy. So, I mean, we got our answer. So the limit of this, even though we couldn't originally solve it, we apply L'Hopital's, we get it. The answer is 2. Okay. Now we're encountering the daunting, well, I'm going to relate this. Delete this, I mean. Hello, okay. This daunting volume-related rates problem. Now, I'm going to cut out part C. Not going to work on that. So part A and B. Oh, man, I think this problem probably take like, honestly, 20 minutes to work through it, even if you're just doing without talking. But so the first problem says, find the volume V of water in the container when H is equal to 5. Cool. Find the volume V. Well, that's interesting. The first thing we notice is that this actually isn't asking for a rate. It's not saying like find the rate of change for volume or like find the rate of change for the water leaving or anything. It's just saying find the volume V when H is 5. And we're given this equation, V equals pi r squared H. So let's not overthink it. Let's just plug H in. So we get V equals, we're trying to find V, right? Pi r squared H is 5. Okay, well, we could solve this, but we don't know R. We don't know R. We need R to solve for V, right? Well, this is where our knowledge of geometry comes in handy. So we're told from the beginning that, hello, where is my, okay. So the cone has a diameter of 10 and it has a height of 10. Now we're told that the height is 5, right? So what is the radius? Well, just knowing geometry, it's going to be proportional. So the diameter is going to be 5, right? Remember, because the height is not 5, the diameter is 5. Previously, the height was 10, the diameter was 10. So if the diameter is 5, then the radius is going to be 2.5, or 5 over 2. So it's multiplied by 2.5. That's so messy. Okay, 2.5. So when we multiply, oh, that's not right. Okay, sorry. We're substituting 2.5 in for R. Yeah, so it's equal to 1/3 pi 2.5 squared times 5 is equal to, hopefully I did that right, last one. So this whole thing is just equal to, I'm just going to solve for this. So 125 over 12 pi centimeters cubed. That's what happens when you multiply this all out. Cool, so we got our answer. The volume is 125 over 12 pi. Wait, what? How come? Okay. Oh, I thought I, okay, so C, don't worry about part C. Okay. So this is our answer. So when H is equal to 5, we know that V is equal to that. Cool. Next, we're looking at problem B. Find the rate of change of the volume of water in the container with respect to time when H is equal to 5. Okay, so now Now we're looking at rates. Now this is where the whole related rates problem, all this implicit differentiation, we want to find d this over d that, d. Now we're looking at rates. So this is where we start doing all that stuff. So find the rate of change of the volume of water. Okay, so let's just look at that first part. Find the rate of change of the volume of water. Okay, so we know what we want to find already. The rate of change of the volume of water, that's just dV over dt. Because remember, dV over dt, this is equal to change in volume over change in time. That's what all this d stuff means. It's all these are derivatives. They're all rates. So change in volume over the change in time. So we want this. We want dV over dt. Once we find dV over dt, we got our answer for part B. We want this. We know, but what do we know already, right? We know that with respect to time, find the rate of change of volume of water in the container with respect to time when h is equal to 5. Okay, well, we know h is 5 for this problem. Let's see. When h is 5, we already calculated in the previous problem. When h is 5, we know r is equal to 2.5. What else do we know? If we read the problem earlier, we're told that the water in the container is evaporating so that the depth h is changing at the constant rate of -3 tenths centimeters per hour. So we're told that dH over dt right now, because this is the rate of change for height over time, dH over dt, we're told the depth h is changing at a constant rate. We're told this straight up -3 over 10. That's constant. It doesn't change. So we're told this rate. They just give it to us. Cool. So that's all we know. Let's start solving the problem, right? Though, when we want to solve the problem, the first question is, well, what equation do we use? Remember, previously we used all these Pythagorean theorem because that makes sense. It was right triangle. But for this, what equation do we use? Well, first instinct, let's look at the equation they give us. This is probably a good place to start. And let's look at it closer. Yeah, this is definitely a great place to start. We want to find dV over dt, HR. We have dV over dt. We want to find dV over dt. There's a volume there in this equation. We have h and r. Well, great. There's an hr here. dH over dt, that's the derivative of h here with respect to time. Okay, it looks like this equation is perfect. And it makes sense. It relates all the variables together. So the equation we're going to use is v equals 1/3 pi r squared h. Okay, well, once we find the equation of interest, what's the first step? First step is always, let's differentiate it. Now let's do some implicit differentiation with respect to time. So d over dt of v is equal to d over dt of 1/3 pi r squared h. Now I would do this. So let's just start. So d over dt of v. Well, the derivative of a variable v is just 1, right? But we are implicitly differentiating, right? Because we're differentiating with respect to t. So it's going to be multiplied by dv over dt. So it's just really dv over dt. So on the left side is dv over dt. Now the right side, 1/3 pi is just a constant. So let's just pull that out. 1/3 pi, let's just do pi over 3 times d over dt of r squared h, right? Because we pulled out the constant of pi over 3. There's a really ugly 3, but there you go. Cool. Now let's take a closer look at this, though. We have d over dt of r squared h, and r squared and h are both two different variables. We have two different variables and they're multiplied with each other. Product rule. We have to do product rule here. There's no other way to just differentiate both with respect to t. We got to use product rule. So in this case, u is equal to r squared, right? Makes sense. R squared is the first one. V is equal to h, u prime, and then v prime. The question is, what is u prime? Remember, obviously u prime, our first instinct is just it's 2r, right? Easy. U prime, v prime. It's just 2r. But remember what we're differentiating against. We're differentiating with respect to t. So if we're differentiating r with respect to t, we can't just leave it as 2r. We're doing a mini chain rule again because it's not the same variable. So it's dr over dt times dr over dt. Remember, anytime we're differentiating with respect to a variable, just multiply it by d whatever over that, the variable that you're differentiating with respect to. So v prime h, power rule gives us 1. But then we have to multiply by dh over dt. Remember, we have to do that because it's all still implicit differentiation. Now we're doing with h. So multiply by dh over dt. Cool. And then we know that product rule is uv prime plus vu prime. Okay, so if we combine all this, dv over dt, right, from the previous step is equal to pi over 3 times u prime times v prime. So u prime is r squared, v prime is dh over dt, so r squared dh over dt plus v u prime. V is h, u prime is 2r dr over dt. Well, I'm just going to multiply h into that, so it'll be 2rh dr over dt. Cool, cool, cool. Now we're given this, and then here's where that whole switch happens where you're like, dang, this problem is freaking impossible. Because let's start plugging stuff in. Let's plug in, okay, we got our equation now, right? This is what we always wanted. So let's plug in and try to solve for dv over dt. So I'm just going to plug it in. dv over dt is equal to pi thirds over r is 2.5, 2.5 squared. dh over dt is negative 3 over 10 plus 2 times 2.5 times h is 5. Oh my, we're almost done. Times dr over dt. Well, what's dr over dt? Oh no, we don't have it in the we know section. All we know is hr and dh over dt. Now it's asking us for dr over dt. They never told us what dr over dt is, and we've never calculated for it because we don't know how. That's why this problem is hard. Because there's a trick that we have to figure out. The trick is here. I'm going to start working on from this point onwards. The trick is that we always knew we never needed to include r in this equation. Because if we look at our previously, we look and we saw that r is half of h here, right? R is, because 2.5 is half of 5. Well, is that always true? Like, yeah, it does seem to be always true because r and h are always proportional, right? So in this case, when h is 10, r would be 5, right? When h is 5, we know that the diameter was 5, so we know that r was 2.5. We already calculated that. So r is actually just half h. So r are big. So I'm going to say can't solve. Let's say we couldn't solve, can't solve. Our big realization is that r is equal to half h. Now let's do it all again. We got to do it all again. Let's start back with our equation. So what equation are we interested in? We were interested in v equals 1/3 pi r squared h, right? Cool, cool. But now we know our secret power is that r is half h. So 1/3 pi half h squared times h. Okay, so what is that equal to? Well, 1/2 squared is 1/4 times h squared, so it would be 1/4, so it would be 1/4 times 1/3, so 1/12 pi h squared times h cubed. Okay, so now we have v is equal to 1/12 pi h cubed. So v is equal to 1/12 pi h cubed. Okay, now let's differentiate this. So d over dt of v is equal to pi h cubed. Is equal to d over dt of 1/2 pi h cubed. Okay, so d over dt of v, again, is dv over dt. We explained that earlier. Now the second part, d over dt, 1/12. Now there's only one variable, there's just h. So now we're really just doing our power rule. Let's bring down the 3. So 3 over 12 pi h squared is equal to 1/4 pi h squared. So dv over dt, made it abundantly clear, is equal to 1/4 pi h squared. Bam, that looks like a nice equation, because what do we have? Let's look earlier. We are told what h is. H is equal to 5. It's given to us in this problem. So that's equal to 1/4 pi times 5 squared is equal to 25 over 4 pi. Did I forget something? Oh my God, I just made the mistake that I always tell people that we can't make. Okay, I totally forgot. Wow. Okay, so we need to go back, because I did a mistake that I've been saying that we can't do. When we're differentiating 1/12 pi h cubed, right? We did the power rule, but remembering we're still differentiating with respect to t. We can't just do power rule. We have to do the whole implicit differentiation step, which is multiplying by dh over dt. Okay, so that's the right answer. The answer is dv over dt is equal to 1/4, because it's still 3 over 12, it's 1/4, but 1/4 pi h squared dh over dt. Well, that's still pretty chill, because we're given h from earlier. We're given h here, right? 5, and we're given dh over dt is -3 over 10. So is equal to 1/4 pi of 5 squared of -3 over 10 is equal to, what is that, 25 over 4 pi times -3 over 10. Am I on the right track with this? Okay, so -75 over 40, right? -3 times 25, -75, 4 times 10 is 40. And that is all equal to dv dt is equal to -75 divided by 5, 15, so -15, 40 divided by 5 is 8, so pi. Well, that's our answer. Can't really get more exact than that, if that's a straight up number. Yeah, I'm not even going to solve for this, what this is exactly, but it's -15/8 pi, and then don't forget the units. The units we've been using are centimeters and hours. So in this case, it'd be the volume is changing at -15/8 pi centimeters cubed per hour. So the rate of change of the volume of water is -15/8 pi centimeters cubed per hour with respect to time when h is 5. We found our holy grail, our dv, oh my God, my handwriting. Our dv over dt. The prize, the treasure we were seeking is that. I think that should be it. So thank you for watching this. I'm going to post these notes. Yeah, have a good night. Bye.